Все, и обратно. Обратно вот так надо возвращаться. Это вот это нажать
Ну,
смену
обратно,
экрана.
да, я даже оттуда у меня обратно. Здесь это то же самое.
Оттуда не взять.
Все.
Да, дальше я даже не знаю, что.
Дальше все, дальше уже начинается ориентироваться.
Дальше вы знаете, да? Как доску включать.
Да. А вы уже запустили трансляцию, да?
По идее, сейчас на игры, наверное.
Ну, нет, запустили, хорошо. Можно уже. Ага. Все, так напомню.
Ну, да, вроде.
Проверим. Ну да.
Работает? Сейчас я тоже проверю.
Я не так быстро. Я вижу,
Ой, скажите, пожалуйста, а в каких числах будете экзамен сдавать?
Экзамен,
Просто
давайте прикинем, значит, где-то, наверное, через недельку буду уже рассылать.
хорошо.
А контрольные?
Контрольные практически вот, ну, там табличка осталась мне вот, перенести все плюсики и минусики, я надеюсь, что, ну, осталось.
Ну, в общем, трансляция работает, вот все.
Ну, значит, можно начинать.
Да.
Okay, so to begin with, let's recall the main results of the previous lecture. So our main object is a locally compact abelian group, G. And as usual, for convenience, we assume that it is second countable. So we constructed a homomorphism between the dual group G hat, which consists of all unitary characters of G, and the maximal spectrum of the Banach algebra L1 of G, or equivalently the space of characters of L1 of G. The isomorphism, this is homomorphism, and it's explicitly it is given as follows: if chi is a character of G, a unitary character, then the corresponding character of L1 of G was denoted by chi tilde. Actually, chi tilde was defined on the bigger algebra, on the measure algebra M of G, and it is given as follows. It takes every measure nu to the Fourier transform of nu evaluated at chi. So this character is defined on the measure algebra, and by the way, it is related to chi by the following simple formula. It takes every Dirac measure concentrated at x to chi of x. So chi can be reconstructed from chi tilde. And we prove that if we restrict chi tilde to 1 of G, then we obtain a bijection, and actually a homomorphism between G hat and the character space of L1 of G. So as a corollary, we deduce that G hat is locally compact for the simple reason that the character space of any commutative Banach algebra is locally compact. And also we observe that this result implies that L1 of G is Hermitian. And this is true because all characters of the form chi tilde, where chi is a unitary character of T, so all characters of the form chi tilde are actually star characters. So since we know that this is a bijection, so all characters of L1 of G are of this form, so they are star characters, and we know that the commutative Banach algebra is Hermitian if and only if all characters of this algebra are star characters. So L1 of G is Hermitian. And next we identified the Fourier transform of G with the Gelfand transform of L1 of G by the following picture. So this is L1 of G. We have the Fourier transform, which takes L1 of G to C0 on the dual group. And we have the Gelfand transform, which takes L1 of G to C0 on the spectrum, on the maximal spectrum. And if we denote this homomorphism by gamma, then gamma induces an isometric isomorphism between these isometric star isomorphism between these two algebras, gamma dot, and we observed that this diagram commutes. This was just an explicit calculation. So as a corollary, the range of the Fourier transform is indeed contained in C0 of G hat, so we automatically get a kind of the Riemann-Lebesgue lemma. And basically this means that the Fourier transform of G and the Gelfand transform of L1 of G are essentially identical objects. And by using this diagram, we proved that the density theorem, which states that the Fourier image of L1 of G is dense in C0 of G hat. Well, indeed, we already know that the Gelfand image of any Hermitian Banach star algebra is dense. And since L1 of G is Hermitian, and since its Fourier transform can be identified with the Gelfand transform, we obtain that this subalgebra is dense in here. Okay. By the way, I forgot to say in the previous lecture about this extra, a little comment about this extra assumption. So of course, we used this assumption of second countability many times. Already the definition of L1 of G, of the convolution of L1 of G was based on this assumption. So the initial question is, how about G hat? Is it second countable? Yes, it is. Let's now prove this simple fact. If G is second countable, then so is G hat. To prove this result, first of all, let's observe that if G is second countable, this implies that L1 of G is separable. Well, this is a simple exercise in measure theory. Basically, if you take a countable base of topology consisting of relatively compact sets, then the respective characteristic functions of the respective sets span dense subspace in L1 of G. So it is separable. On the other hand, a standard fact from functional analysis is that if E is a separable Banach space, then the unit ball of the geospace E star, so we know that it is weakly star compact by the Banach theorem. But we can say more, it is not only compact, but it is also metrizable under the assumption that E is separable. So it is compact and metrizable. And it's a standard fact that every compact metrizable space is separable. Just this is a standard argument involving epsilon nets. So it is separable and metrizable. And a separable metrizable space is a second countable. If we now come back to G hat, we see that we know that G hat is identified with the character space of L1 of G, so it is topologically embedded into the unit ball of the dual to L1 of G with the weak star topology. So this is second countable, and this implies that G hat is also second countable. Okay. Our next goal is to prove the uniqueness theorem for the Fourier transform, which states that the Fourier transform is always injective. First of all, let's introduce some terminology. Suppose that A is a star algebra and H is a Hilbert space. By definition, a star representation, representation of.
A is not assumed to be commutative.
No, the definition doesn't depend on the commutativity, just any star algebra. Actually, we don't assume that A is equipped with a norm. It's just a pure algebraic object. So a star representation of A is just star homomorphism, say pi, from A to the algebra of bounded linear operators on H. And we say that pi is faithful. Pi is faithful if it is injective, that is, if its kernel is trivial. So now we have the following lemma. Lemma 1. Which gives us useful sufficient condition for the injectivity of the Gelfand transform. Suppose that A is a commutative Banach star algebra, and suppose that A has a faithful star representation on a Hilbert space. I claim that the Gelfand transform of A is injective. Well, indeed. Let's take a faithful star representation, pi, from A to B of H. A faithful star representation. By the way, let's recall that it is automatically continuous. Any star homomorphism from a Banach star algebra to a C star algebra is continuous, and its norm is at most 1. So we take a faithful star representation and let B denote the image of, or better, the closure of the image of pi. So clearly B is a commutative C star algebra. A commutative C star algebra, because it is a closed star subalgebra in DOH. It's a star subalgebra because pi is a star homomorphism. So it is isomorphic by the Gelfand-Banach theorem. It is isomorphic to C0 of X, where X is the maximal spectrum of B. And in particular, this implies that characters of B separate the points of B. Which is clear because, evaluation characters on C0x separate the points of C0x. And if we now compose such characters with pi, we get some family of characters of A, which separates the points of A. This implies that characters of A separate.
What's X again?
X is the maximal spectrum of B. But at this point, this is not essential, because what we want is that we want that B has many characters. And C0S always has many characters. But of course, X is the maximal spectrum of B. So characters of A separate the points of A, because pi is injective. But this last line means precisely that the Gelfand transform is injective. Let's recall that the kernel of the Gelfand transform is the intersection of the kernels of all characters. So characters separate the points, and so the only element which sits in the intersection of their kernels is 0. So the Gelfand transform is injective. Okay, we want to apply this lemma to L1 of G. To do it, we need to construct faithful star representation of L1 of G. And this is quite easy. This is our lemma 2. Suppose that G is a orderly compact abelian group. Second countable as usual. Then, first of all, I claim that if f is a function in L1 of G, and G sits in L2 of G, then their convolution is defined almost everywhere. Belongs to L2. Belongs to L2 of G. And the L2 norm of the convolution of f and G is less than or equal to the product of the norms of f and G. So we know this is true if f and G are both in L1, but the same fact is true if f sits in L1 and G sits in L2. And the second part of the lemma states that we have a faithful star representation of L1 of G on the Hilbert space L2 of G. And this representation is given by the following simple formula. The operator lambda of f is the convolution operator. It takes every G to the convolution of f and G. So I claim that lambda is a faithful star representation. Well, the proof of part 1 is an exercise for you. Basically, the proof is almost identical to the case where we convolve two functions in L1. The idea is exactly the same, modulo some cosmetic changes. As for the second part, the fact that lambda is a star representation is very easy. This is just an explicit calculation. Lambda is a star representation. This is an exercise. This is quite straightforward. So why is it faithful? Why is it faithful? Well, we know that L1 of G has an approximate identity. And moreover, we can always choose an approximate identity consisting of continuous compactly supported functions. Actually, we can construct a Dirac net consisting of continuous compactly supported functions. So let's choose such an approximate identity. Let E alpha be an approximate identity of L1 of G contained in the space of continuous compactly supported functions. And let f belong to the kernel of lambda. Then, since E lambda is continuous and compactly, E alpha is continuous and compactly supported, it sits in L2. So lambda of f applied to E alpha is 0. That is, the convolution of f and E alpha is 0. for every alpha. But on the other hand, E alpha is an approximate identity in L1 of G, so this necessarily converges to F. And that's it. So this shows that F is 0. Okay, so this completes the proof of lemma 2. And now combining lemmas 1 and 2, we obtain the following important result, which is usually called the uniqueness theorem. For the Fourier transform. So this result states that the Fourier transform of any locally compact abelian group is injective. The proof is immediate from lemmas 1 and 2. L1 of G has a faithful star representation, and now applying lemma 1, we deduce that the Gelfand transform is injective. But on the other hand, we already know that the Gelfand transform of L1 of G can be identified with the Fourier transform. So it is injective. As an important corollary, we see that unitary characters separate the points of G. G hat separates the points of G. So explicitly this means that for every element in G different from the identity, you can always find a unitary character chi such that chi of x is not equal to. If we now have two distinct points x and y, we can consider the element x inverse y and find such a character, and so we see that indeed chi of x is not equal to chi of y. To prove this corollary, let's choose a continuous compactly supported function f such that it separates the identity and element x inverse. Of course, this is always possible because continuous compactly supported functions separate the points. We know that the Fourier transform is injective, and of course f is not identically 0, so we can always find a character of L1 of G which separates the following two functions. So this inequality, I forgot to say that they are not equal, of course. If we look at the left translate of f and f, then they are not the same, of course, because if we evaluate both them at the identity, we get this. So these functions are not the same, and so we can separate them by a character of L1 of G. But characters of L1 of G come from unitary characters of G. So this implies that there is a unitary character chi of G such that the respective character chi tilde separates LXF from F. Is not equal to. But what is chi tilde applied to LXF? Well, LXF is the convolution of the Dirac measure delta x and F. And chi tilde is also a character of the measure algebra. So this is the product, chi tilde of delta x and chi tilde of f. And chi tilde of delta x is just chi of x. So now comparing these two numbers, so they are not the same, we see that chi of x is not equal to 1. let's approve. Okay, now it's the next step towards the main results of commutative harmonic analysis, that is, towards the Planck-Rayleigh theorem and to the contracting duality. Let's discuss positive definite functions. Positive definite functions. And Bochner's theorem. This is a quite important subject, and we will see that it is very helpful in our approach to the Planck-Rayleigh theorem and to the contracting duality. To begin with, let's define the notion of a positive linear functional on a star algebra. Suppose that A is a star algebra, and suppose that omega is a linear functional on A. We say that omega is positive, and write abbreviate this as follows. If omega applied to A star A is always non-negative for every element of our algebra. It's useful to introduce a special notation for the set of all positive linear functionals. We are especially interested in the case where A is Banach star algebra. So if A is a Banach star algebra, then the set of all bounded positive linear functionals on A will be denoted like this. So this is the set of all omega in A star, such that omega is positive. Of course, this is not a vector subspace, it's just a set. Clearly, the sum of two positive functionals is positive, and if you multiply a positive functional by a non-negative number, we get a positive function. But on the other hand, if omega is positive, then minus omega is not. So it is the set of positive functionals is a convex cone. Oh, this is a convex cone in this. Let's look at some concrete examples of positive functionals. Example 1. First of all, let's observe that every character is positive. Every star character, if chi is a star character, then if we evaluate chi at A star A, what we get is the absolute value of chi y squared. And of course, this is non-negative. So we deduce that every star character is positive. Example 2. Let X be a locally compact Hausdorff topological space. And let's look at the algebra C0 of X of continuous and vanishing ad infinity functions on X. What can we say about positive functionals on this algebra? Well, the Riesz Markov-Kakutani theorem easily gives us an answer. So I claim that there is a bijection between the set of all positive linear functionals on C0 of X and the set of all finite positive random measures on X. Well, let's denote the set by M of X positive. So M of x consists of all complex Rodel measures, and this is a subset consisting of all positive Rodel measures on X. Well, this is almost immediate from the Markov-Kakutani theorem, which states that the dual of C0 of X consists of all complex Rodel measures. The only thing to check is that the functional corresponding to a measure is positive in the sense of this definition, even though if the measure is positive in the usual sense. But this is quite easy. Well, indeed, if mu is a complex Rodel measure, let's denote by I mu the integration with respect to mu and I mu is positive, even only if we substitute here some function f for some function f, we substitute f star f here. So then this is just the integral of the absolute value of f squared, and this must be non-negative for every f in C0 of x. But it's a simple exercise in measure theory to show that this happens even only if mu is positive in the usual sense. Okay. Example 3. Suppose that H is a Hilbert space, and suppose that A is a star subalgebra in B of H. Star subalgebra. Then, for every vector V in H, we can consider the following functional omega V on A, given by the following formula. It takes every operator T to the inner product of TV and V. So clearly this is a bounded linear functional, and if we calculate omega V at T star T, so we must substitute T star T here, then we move T star from here to here, and we get what we get is just the inner product of TV by itself, that is the square of the norm of TV. Clearly this is non-negative, and so our function is positive. Example 4, and this is an exercise at the same time. This example is closely related to harmonic analysis. Suppose that A is the group algebra of an arbitrary group G, or we can also take the little one algebra. So here G can be any group. Or we can also take, if G is a locally compact group, we can take the convolution algebra consisting of continuous compactly supported functions. So we equip this algebra with the convolution product and consider it as a star subalgebra in O1 of G. G is a locally compact abelian group. Oh, not necessarily abelian actually, just a locally compact group. And define the following functional, omega, which is just the evaluation at the identity. And the calculation shows that the functional is positive. Omega is positive.
G is any group, right?
If we consider the group algebra or little one of G, then G can be any group. And if G is a locally compact topological group, then we can consider continuous compactly supported functions.
Okay.
Okay, let's now observe that every positive functional on any star algebra generates something like an inner product on this algebra. So let's introduce some notation. Suppose that A is a star algebra and omega is a positive linear functional on A. For every two elements A and B in our algebra, let's introduce the following number defined as omega applied to B star A. So this is a function of two variables. And clearly this is a sesquilinear form. This is a sesquilinear form. In the sense that it is linear in A and anti-linear, conjugate linear in B. Well, if we restrict this form to the diagonal, this will be omega applied to A star A, and omega applied to A star A is non-negative, because omega was assumed to be positive. And in particular, this number is real for every A. And it's a simple standard algebraic exercise to show that if a sesquilinear form is real on the diagonal, then it is Hermitian. This form is Hermitian. That is, if we interchange the variables A and B, then we have the following identity. This is equal to the conjugate of AB, or all A and B. So in summary, we see that this form is a semi-inner product. Semi-inner product. So what is a semi-inner product? This is almost an inner product, with the only exception that the inner product of an element by itself, of a non-zero element by itself, can be equal to 0. But all other axioms of an inner product are satisfied. And any semi-inner product on a vector space satisfies the Cauchy-Banach inequality. The Cauchy-Banach inequality, which in this case looks as follows: omega applied to B star A. So the absolute value of this number squared is less than or equal to omega A star A times omega of B star B. We will be interested in positive linear functionals on the algebra L1 of G, where G is a locally compact abelian group. Before we describe such functionals, let's introduce the following pure algebraic notion. That is the notion of a positive definite function on a group. We start with a pure algebraic situation. That is, with a situation where G is just a group, not equipped with any topology. And suppose that phi is a function on G, a complex valued function on G. Then, for every n tuple, for every natural number n, and for every n tuple of elements of G, say x1 to xn, we define a sesquilinear form that's denoted by b phi x. This will be a sesquilinear form on the finite dimensional space Cn. So we define it as follows: phi x of u v is equal to the following sum: little phi of xj inverse xi ui vj conjugate. So this is clearly this is a successfully uniform on Cn. We say that our function little phi is positive definite in Russian положительно определенная. If for every natural n and for every n tuple of elements x of G, the sesquilinear form phi x is positive definite in the sense that its restriction to the diagonal is non-negative. Phi x applied to u is non-negative for every u and in Cn. Well, let's now make some observations. Let's observe some properties of positive definite functions. First of all, let's observe that if we evaluate phi at the identity, then this is non-negative. To see this result, it suffices to let n equal 1. If n equals 1, we get precisely this inequality. Well, second, if, by the way, here, so here from now on, we suppose that little phi is positive definite. Then phi v is non-negative. Second, we observe that since this form is positive definite, exactly as in the case of positive functions, we deduce that this form is phi x is a semi-inner product. On Cn. And in particular, this Hermitian, that is phi x applied to v and u, is a complex conjugate to phi x applied to u and v. And also it satisfies the Cauchy-Banachowski-Schwarz inequality. Phi x of u squared is less than or equal to the following product. Let's look at a special case where n equals 2. So let n equal 2. And let's take the following pair of elements of G, where the first coordinate is just the identity of G, and the second element is arbitrary. Let u and v be two vectors of the standard basis of C2. So the matrix of this sesquilinear form with respect to this basis is given by the following formula. We have phi of E add to the diagonal. Here we have phi of S, and here we have phi of S inverse. Now, by looking at this quality, so we know that this form is Hermitian, and for these concrete u and v, we see that these two numbers are complex conjugate to each other. So formula 2 implies that phi of S inverse is phi of S complex conjugate. And the Cauchy-Pirkovskii-Schwarz inequality in this case looks as follows. So phi applied to in V is this element, just phi of S. So phi of S squared is less than or equal to the product of two off-diagonal elements, so this and this. But we already know that they are complex conjugate to each other. So the product is oh, sorry, not off-diagonal, just the other way around, of two diagonal elements of this matrix. That is phi of E squared. So that is just, this means just that phi of S is less than or equal to phi of E. And in particular, we see that the function phi is bounded. Or phi is bounded. Well, let's look at some examples of positive definite functions. First of all, I claim that a unitary character is always positive definite. Unitary character. Well, indeed, if we look at our form, so it is given by this formula. If we substitute here our character, what we get is the following sum. Chi applied to xj verse xi, ui, uj complex conjugate. So chi is unitary character, so this is equal to chi of xj conjugate, chi of xi, ui, uj conjugate. Because chi is a unitary character. Now this is nothing but the square of the absolute value of the following sum, which is non-negative. So we deduce that every unitary character is positive definite. More generally, let's suppose that we have a Hilbert space H, and let's denote by U of H the unitary group of H, which consists of all unitary operators on H. And suppose that we have a unitary representation, pi of G, unitary representation that is just a group homomorphism from G to U of H. Then, for every vector v in H, we can consider the following function, pi v on G, which is given by the following formula. This is the inner product of pi of x applied to v and v. Well, a simple calculation, and which this calculation is an exercise for you, shows that this function is positive definite. An important fact is that actually every positive definite function on G arises in this way. That is, it comes from a unitary representation. The respective construction is due to Gelfand, Limerick, and Siegel. So it is usually called the GNS construction. So GNS is for Gelfand, Limerick, and Siegel. Unfortunately, for time reasons, I have to skip this construction because it is not directly related to our course. It is very important in representation theory. But now we are mostly interested in the abelian case. And in this case, we can do without this result. So for us, this is just an example of a positive definite functions, for a positive definite function. It's useful to introduce a special notation for the set of all positive definite functions. Let's denote it by P of G. Actually, there is no standard notation. So let's denote it by P of G. Set of all positive definite functions on G. So clearly it's a positive kernel in the set of all functions. So the sum of two positive functions is positive definite functions is positive definite, and if we multiply a positive definite function by a non-negative number, we get a positive definite function. So let's now find a relation between positive definite functions on G and the positive functionals on the group algebra of G. So let's take the group algebra of G. It will be convenient to identify this algebra with this algebra of all finitely supported functions. Finitely supported functions on G. And we equip this algebra with the convolution multiplication. So as a vector space, it is spanned by delta functions concentrated at points of G. This is a vector space basis of this algebra. So the multiplication is the convolution. It is uniquely determined by the following formula. So it extends the multiplication in G. And the involution, it's a star algebra. The involution is uniquely determined by the following relation. So it is a star algebra.
Сейчас мы разбираем функции, которые не нулевые в конечном числе точек.
Да. Ну, групповая алгебра, она же просто состоит из конечных линейных комбинаций, вот таких формальных линейных комбинаций. So the group algebra consists of formal linear combinations of elements of G. So the group itself serves as a basis of this space. And if we identify it with the span of delta functions, so delta is concentrated at x, it is equal to 1 at x and 0 elsewhere. And of course, a linear combination of such functions is nothing but a function which is finitely supported. So it's 0 outside a finite set. So this is star algebra. And I claim, this is a rather simple, not useful result. So before I state this result, let's look at the dual space, the algebraic dual space of this algebra. So let's observe that there is a vector space isomorphism. There is a vector space isomorphism between, let's note it by alpha, between the space of all functions on G and the dual of the group algebra. Of course, here I mean the algebraic dual. So this is not normed algebra. Consider all linear functionals on CG. So this isomorphism takes every function phi on G to the functional alpha phi, where alpha phi is uniquely determined by the following formula. It takes delta x to phi x. Well, Well, this is more or less clear. This is actually a very simple exercise in linear algebra. Okay, now how about positive functionals on the group algebra? The answer is given by the following proposition. The functional alpha phi is positive, even only if the function phi is positive definite. So this proposition shows a relation between two kinds of objects, positive functionals and positive definite functions. The proof is very easy, just an explicit calculation. So suppose that f is an element in the group algebra. So we can write f as a finite linear combination of the following form. Then f star is, so we must take the complex conjugate of every coefficient and replace xi by xi inverse. So for convenience, we take another index, another summation index j. And then alpha phi applied to f star f. So we must take the convolution of f star and f. And the convolution is the sum over I and j. Ci, Cj conjugate delta xj inverse xi. And after we apply alpha phi, we get the following sum. Ci, Cj complex conjugate. And this is exactly the sum which appears in the definition of a positive definite function. So by definition, phi is positive definite, if and only if this is always non-negative for any choice of elements in our group and for any choice of constants Ci. But on the other hand, this is positive if and only if this function is positive. So this completes the proof. By the way, let me remark, this is not exactly a corollary, this is rather a corollary of the proof. Let's observe that phi is positive definite, even only if the respective ciscollinear form, big phi x, is positive definite for every n tuple x1, xn of pairwise distinct elements. Or G. Well, indeed, in our original definition, we consider arbitrary n tuples. But on the other hand, of course, delta functions form an algebraic basis of the group algebra. So here, we may assume that they are pairwise distinct, and we get the same formula. So this is positive if and only if this is positive under the assumption that they are pairwise distinct. So this is an equivalent, a very similar but equivalent definition of a positive definite function. Let's now assume, so far G was an arbitrary group. Let's now assume that G is finite and abelian. This will be just an illustration, but in my view it is rather helpful. Suppose that G is a finite abelian group. Then, the set of all positive definite functions on G consists exactly of linear combinations of unitary characters with non-negative coefficients. actually, it's more or less clear that the right-hand side is contained in the left-hand side, because every character is positive definite, and such a non-negative combination of positive definite functions is positive definite. So we want to show that they are equal. Why is it so? In my view, the shortest way is to apply the Fourier transform. So we know that the Fourier transform on a finite abelian group is actually an isomorphism between the group algebra of G and the algebra of all functions on the dual group G hat. So this algebra is equipped with the pointwise multiplication. And this is a star isomorphism. The Fourier transform is a star isomorphism. So the dual map is a vector space isomorphism. The dual map is vector space isomorphism. This is F star. But we already know that the right-hand side is nothing but it is isomorphic to the space of all functions on G, and if we restrict this to positive functionals, then this will be a bijection between these two sets. But positive functionals on the group algebra are identified with positive definite functions on G by the previous proposition. And what is the dual of, what is the set of positive functionals on the algebra of all functions on G hat? Well, we may interpret this as the algebra of continuous functions on G hat, because G hat is just a finite group, and particularly is compact. So this is the set of all positive measures on G hat. But what is a positive measure on a finite set? Well, a positive measure on a finite set, of course, is a finite combination of Dirac measures with non-negative coefficients. So now to compute the proof, it's enough to observe that the Fourier transform, the dual of the Fourier transform F star, takes every delta function delta chi, Dirac measure delta chi, to chi. This is a little calculation, a simple exercise for you. And this completes the proof. So this set under this bijection goes precisely to this one.
How did we obtain the third line?
Which one? This one? This one. Well, F is a star isomorphism, so it induces a bijection between positive functionals on this algebra and positive functionals on this algebra. So, applying this proposition, we see that positive functionals on the group algebra are identified with positive definite functions on G. This is the algebra of, let's look at this algebra as the algebra of continuous functions. This is the algebra of continuous functions on G hat. We know that positive functionals, well, let's look at the respective example. Positive functionals on C0 of x, if x is compact, this is just C of x, is nothing but the set of all finite positive Radon measures on the space. But here we are in a very simple situation where x is finite. So our x is finite, our x is G hat. So positive measures, a complex measure on the finite set is just a linear combination, arbitrary linear combination of Dirac measures. And this measure is positive if only if the coefficients in this decomposition are non-negative. C high is just the measure of a single point. By the way, this proposition can also be easily proved without using the Fourier transform. This is a nice exercise. Give a proof which avoids using the Fourier transform. It's rather straightforward, but it's considerably longer. It involves some extra calculation. Okay, now let's look once again at this proposition, which relates positive functionals on the group algebra with positive definite functions on G. Our next goal will be to extend this result. Well, not exactly extend, but prove a similar result for the algebra L1 of G, where G is a locally compact group. Surprisingly enough, it turns out that the description will be very similar. So, of course, if G is a locally compact group, then the group algebra, the algebraic group algebra of G, and the algebra L1 of G are different. The algebraic group algebra consists of finite linear combinations of Dirac measures, and L1 of G consists of integrable functions. So if G is not discrete, then the group algebra is not a subalgebra in L1 of G. Nevertheless, positive linear functionals on L1 of G are also described in terms of positive definite functions. This will be our next goal. Oh, sorry. Next page is here. Okay, so from now on, G is a locally compact topological group. Again, as usual, we assume that it's second countable. And we denote by mu a higher measure, G. First of all, let's recall that standard result of functional analysis that there is an isometric isomorphism of Banach spaces between the space L infinity of G and the dual of L1 of G. An isometric isomorphism of Banach spaces. Which looks as follows. It takes every essentially bounded measurable function phi to the functional alpha phi, where alpha phi is given by the following formula. So if we want to describe positive linear functionals on L1 of G, well, they will correspond to some functions in L infinity of G. Such functions are called functions of positive type. So we say that a function phi in L infinity of G is a function of positive type. If the respective functional alpha phi is positive. And let's introduce the following temporary notation. Better I do it on the left board. We denote by P infinity of G, the set of all functions of positive type on G. So we view this set as a subset in L infinity of G. So two functions are the same in this. The two functions represent the same element of the set if they agree almost everywhere. And similarly, we denote by P of G the set of all continuous positive definite functions. Continuous positive definite functions on G. So this is compatible with our early notation for P of G, because if G is not equipped with the topology, we can make it into a locally compact discrete locally compact topological group. So all functions will be continuous. So this generalizes P of G, which was considered when G was not was just a group, not a topological group, but just a group. I've already said that this notation is temporary, and it is temporary because we will see shortly that actually these two sets are essentially the same. So to begin with, let's prove the following result. Suppose that phi is a continuous bounded function of G. Then phi is of positive type, if and only if phi is positive definite. So we see that assuming that phi is continuous, the respective linear function is positive, even only if phi is positive definite, just like in the pure algebraic case. Before proving this theorem, let's look at two lemmas. Lemma exercise 1. This lemma gives another characterization of functions of positive type. More precisely, if phi is an arbitrary function in L infinity of G, and f and g are two functions in L1, then the functional alpha phi applied to G star f can be calculated as follows. This is the integral over G cross G by y inverse x, f of x, f of y conjugate. This is just an explicit calculation. Substitute write an explicit formula for the convolution of G star and f, multiplied by phi, take the integral, so applying several times, using several times the left invariance of the higher measure, and using the forbidden theorem, if you like, you come to this formula. This is quite automatic. It's instructive to compare this formula with the sesquilinear form, which appears in our definition of a positive definite function. So let's compare. Where is it? It's not here. I'm looking for the sesquilinear form, which appears in the definition of a positive definite function. Unfortunately, it's on this board. Nevertheless, let's look at it. So look here. So I hope you remember, and compare with this. Looks similar, I hope. So this looks like an integral form of an integral analog of the sesquilinear form, which appears in our definition of a positive definite function. Sorry, this is G, of course. Sorry, G1. G of I complex conjugate.
Тот же со звездочкой подразумевается в смысле элемент из бесконечности?
No, G star is he will use the fact that L1 of G is a star algebra. This is an evolution on L1 of G. By the way, let's call it the formula. J star of x is J of x inverse complex conjugate and multiplied by the modular character delta of x inverse. This is the explicit formula for the evolution on L1 of G. Okay, so in view of this lemma, this theorem becomes not so surprising. So this, since the definition of positive definite function involves essentially the same number as here. If you substitute here f by f star, so the positivity of this integral is very similar to the positivity of the respective subscripting form on Cn. Lemma 2, lemma exercise 2. Let's choose a base, beta, a base of relatively compact symmetric neighborhoods of the identity in our group G. And let's choose a Dirac net indexed by beta, a Dirac net in L1 of G. So let's recall the definition. This means that every function uv is non-negative. It is concentrated on v, in the sense that it vanishes outside v, and its integral is 1. Its integral is 1.
Это называется дельтаобразное расследование.
Yeah, in Russian, standard terminology is delta-образная направленность. If it is countable, then it is delta-shaped sequence. Then, I claim that first of all, for every continuous and bounded function phi on G, the integral of their product uv and phi converges to phi of E. In particular, this convergence implies that uv itself, if we consider L1 of G as a part of the measure algebra, then this net converges to the Dirac measure concentrated at the identity. Weakly star converges weakly star in the measure algebra M of G. This is a special case of the previous convergence, because formally the weak star convergence is this convergence for every function phi in C0 of G. But I claim that it actually holds for every continuous and bounded function phi. By the way, this convergence explains the terminology. It explains why Dirac nets are so called. They converge weakly star to the Dirac measure concentrated at the identity. And part 1, if we consider the tensor product of uv by itself, so this will be a function on G cross G, and this net will be a Dirac net in L1 of G cross G. As usual, we use the standard tensor notation. So uv tensor uv means this is a function which takes x and y to uv of x, uv of y. This is more or less immediate from the definition. Actually, it is supported on v cross v and positive, and its integral is 1. So this is just a simple observation. Okay, let's now prove our theorem. First of all, let's prove the left-to-right implication. So we assume that phi is of positive type, and let's prove that phi is positive definite. So we take an n-tuple of elements in G, x1 to xn. We take an n-tuple in Cn of complex numbers, t1 to tn. And let's consider the following function. So first of all, we choose a Dirac net. Choose a Dirac net, uv. L1 G.
Что там с ним рисует?
G1, sorry, this should be n, an element in Cn. And this is a comma. Let's consider the following function, fv. This is the following finite sum, ti, and we take the left translate of uv by xi. So this is roughly the idea is that this function is a substitute for the finite linear combination of Dirac measures concentrated at xi when we constructed bijection between positive definite functions on a group and positive functionals, we considered such functions. So here is the idea is basically the same, but of course we cannot consider Dirac measures because they are not functions in L1 of G. Instead of that, we take something like an approximation to this function. So this is fv, for the fv in beta. By assumption, phi is of positive type, so if we apply alpha phi to fv star times fv, then this is non-negative. Let's now write this explicitly by using level 1. Fv star is the following sum over j, tj conjugate lxi uv star. So by using the linearity, we take the double sum over I and j, tj conjugate ti, and then we apply alpha phi to the convolution of this function and this function. And by level 1, this is the following integral. Phi of y inverse x. So we must then evaluate this function at x, which is the same as phi evaluated at xi inverse x. Not phi, uv evaluated at this point. Then uv evaluated at xj inverse y, and then we integrate this over g cross g. This follows from level 1. Well, let's now use the left invariance of our measure, for our Dirac measures. Of the Harmonic measure. We translate x by xi on the left and y by xj on the left. Then we get the following sum, tj conjugate ti, the integral over g cross g. So now y is replaced by xjy. X is replaced by xix. Uv of x, uv of y. Okay. So this is just nothing but the tensor product of UV by itself, and this is a Dirac net in this algebra. Particularly, it is an approximate identity. So we see that the whole sum converges to what? To the sum over I and j. So we must just evaluate this function at the identity. We substitute here the identity for x and y, and we get phi evaluated at xj inverse xi ti tj conjugate. Okay, so this is exactly the expression which appears in the definition of a positive definite function. And since all these integrals are non-negative, the limit is also non-negative. So phi is positive definite. Okay, now let's now prove another implication. So we now suppose that phi is positive definite. Phi is positive definite. And we want to show that it is of positive type. Actually, it suffices to show that the respective function is positive on the dense subalgebra consisting of continuous functions of continuous compactly supported functions. So it suffices to show that alpha phi applied to f star f is non-negative for every continuous compactly supported function f on G. For the simple reason that this is dense in L1 of G. So if this is true for such functions, that it is automatically true by continuity for functions in L1 of G. Okay, so let's take a continuous compactly supported function f. Let k denote the support of f. And for convenience, let's denote the function which appears in lemma 1, this function, by big F. This y inverse x, f of x, f of y conjugate. So we want to show that the integral of big F is non-negative. Let's observe that f big F is also continuous and compactly supported on G cross G, and its support is contained in K cross K. So this implies that we can approximate f by a suitable step function, and this is a little exercise for you. For every positive epsilon, we can always find finitely many disjoint Borel sets. Disjoint Borel sets U1 to n, and points xi in ei for every I, such that K decomposes into the union of these sets, so they form a partition of K, and such that F is uniformly close to the following step function over I and J. So this number is multiplied by the characteristic function of EI cross EJ. So this we can find such a function in such a way that this supremum norm is less than epsilon. A hint is just to use the uniform continuity of F. Uniform continuity of F. So first you cover K by a finite union of translates of a suitable neighborhood of the identity, and then you remove pairwise intersections from of these translates of the neighborhood, and you get the partition E1 to En. Okay, so by using this approximation, let's denote this, for convenience, let's denote this function by g epsilon. By using this approximation, we can now approximate the integral f by the integral of g epsilon. Well, indeed, the absolute value of this number can be estimated as the integral of f minus g epsilon. It suffices to integrate over k cross k because both functions f and g epsilon are supported on k cross k. So this is less than or equal to the supremum norm, that is epsilon, times the measure of k cross k. And the measure of k cross k is a constant mu of k squared. On the other hand, if we calculate the integral of g epsilon, g epsilon, this is a step function, so this integral is just the following double sum over I and j. F of xi xj times the measure of ei, the measure of ej. And if we substitute here big F, we get the sum over I and j, phi evaluated at this point, times f evaluated at xi, here I also multiplied by the measure of ei. Next we have the complex conjugate of f evaluated at xj, and we multiplied also by the measure of ej. Okay, so this is our integral. Let's recall that the original phi was assumed to be positive definite. And since it is positive definite, we look at this expression and we see that it is non-negative. And that's it. So this shows that our integral of f can be approximated by a non-negative number. So it is non-negative itself. Since epsilon was arbitrary, we deduce that the integral of f is non-negative. The integral of f is non-negative, and this means precisely that phi is of positive type. And this completes the proof. Okay, so let's look at the statement once again. Here we assumed from the very beginning that phi is bounded and continuous. Of course, the assumption of boundedness is quite natural because the function, a positive definite function, is always bounded. And the function of positive type is essentially bounded, just by the definition. But the continuity of phi was quite essential. Well, indeed, if g is not discrete, then normally we can find many discontinuous positive definite functions, like, for example, discontinuous characters. There are many discontinuous characters of the real line, and they are badly behaved. So, of course, if we have a discontinuous character, then there is no hope to describe it as a positive function on L1 of G. On the other hand, we will see soon that if phi is a function of positive type, then it is essentially continuous, in the sense that it is almost everywhere equal to a unique continuous positive definite function. Or more exactly, this result is true for any locally compact group, but we will prove it for locally compact Abelian groups. Okay, so our next goal will be to describe positive functionals on L1 of G, where G is locally compact Abelian group, in terms of measures on the dual group. So the prototype of this result, the respective result, is here. So if G is a finite abelian group, we already know that positive definite functions can be described in this way. So they are related to positive measures. Actually, they are in a one-to-one correspondence with positive measures on the dual group. It turns out that a similar result holds for any locally compact abelian group. To prove this result, it will be first of all convenient to introduce the so-called dual Fourier transform.
Извините, кажется, через 5 минут уже следующий пар начнется.
Вы намекаете на то, что лучше, наверное, на этом остановиться, да? Окей, let's stop here.
Я уже приедет.
А?
Я уже, по крайней мере, на кредите.
Окей.
Мы на 20 минут задержались, на 25.
Когда мы 20 минут задержались? Почему на 25?
Что у нас 20 заканчивается.
Прошу прощения. Of course, we have to stop here. Sorry, I
Можно последнюю?
thought it would...
Можно последнюю страницу?
Да, пожалуйста. Я просто думал, что почему-то, что начало у нас в 13:30, поэтому болтаю, а на самом деле должна заканчиваться. Okay, so that's all for today. At the next lecture, we will prove Bochner's theorem, which interprets positive definite functions on a locally compact abelian group in terms of positive measures of the dual group. As a corollary, we will see that every function of a positive type is essentially continuous. Да, теперь надо остановить эту штуку, да?
А это можно вообще сделать.
Сделайте, да? Хорошо. Все, еще раз, извините, я почему-то как спали, как начинается в 11:30, я уже отчитываю, когда будет без 10. А может вовсе не 13:30, а 13:16. До свидания.
До свидания.
Я подумал, может, так важно материал, когда уже дальше пошло, надо сказать.
Понимаешь, это вот как...
Не 10 лет.